Most stars are loyal. Born inside a galaxy, they spend their entire lives bound to it, making slow, multi-million-year laps around the galactic center. But every so often, a star breaks the rules. We find them tearing through space at millions of kilometers an hour, escaping their galaxy entirely. There is one escaping star in particular, a massively heavy, fast-burning star known as HE 0437-5439. Right now, it's out in the dark halo of the Milky Way, falling toward us across intergalactic space. A star moving at that velocity requires a specific physical explanation. Its speed is a direct measurement of the violence required to launch it, and that motion carries a memory of exactly what happened. For decades, the assumption was simple. Trace the path of an escaping star backward, and it should lead straight home. It should point directly to Sagittarius A star, the 4 million solar mass black hole waiting at the center of the Milky Way. To test that, astronomers turned to Gaia, a European spacecraft mapping the three-dimensional positions of over 1 billion stars. With that data, you can take a fleeing star and rewind its multi-million-year journey. But when researchers rewound HE 0437-5439, the line didn't lead home. It missed the center entirely. Instead, the path pointed across 100,000 light-years of empty space, leading directly to a neighboring cluster of stars called the Large Magellanic Cloud. This is a dwarf galaxy. It is only 1/10 the size of the Milky Way, and astronomers had long assumed it was far too small to hide a giant black hole. But if our central black hole didn't throw this star, the path points elsewhere. A supermassive object must be hiding inside our tiny galactic neighbor. To understand why a black hole is required here, you have to look at the physics of the launch. To hurl a massive star at over 6 million kilometers an hour requires an extreme, violent gravitational slingshot. It requires something called the Hill's mechanism. Picture two stars, born together, a binary pair, locked in a tight orbit and dancing through space as a single unit. Over millions of years, that pair wanders just a little too close to a supermassive black hole. The black hole pulls harder on the near star than the far star, and that extreme tidal stretch begins to warp the partnership. The gravity is strong enough to rip the partnership apart entirely. One of the two stars gets captured, falling into a tight, permanent orbit around the black hole as a prisoner. But energy has to be conserved. As a cosmic receipt for that capture, the black hole violently hurls the other star outward, blasting it away into deep space. One star imprisoned, one star exiled. Each of these stars carries the exact physical memory of a black hole encounter in its speed and its trajectory. And HE 0437-5439 is not an isolated case. When the research team traced a larger sample of runaway stars, roughly half of their confident traces pointed back to the Large Magellanic Cloud. But there was a noticeable difference in how they arrived. The stars coming from our smaller neighbor were traveling significantly slower, on average, than the ones thrown by our own galaxy. This chart compares the ejection speeds from the two galaxies. The Milky Way's massive engine generates the higher speeds shown on the left, but the gentler launch from the Large Magellanic Cloud points to a smaller engine. Calculating that difference reveals a hidden black hole roughly 600,000 times the mass of our Sun. There was one final detail. When mapped in our sky, these runaway stars from the Magellanic Cloud aren't scattered randomly. They are all bunched together in a small patch near the constellation Leo. That bunching is actually a signature. The Large Magellanic Cloud is actively orbiting the Milky Way at hundreds of kilometers a second. When its hidden black hole throws a star, the star inherits the forward momentum of the moving galaxy that threw it. The calculated speeds and the clustered trajectories line up perfectly. It is the fingerprint of a moving launcher, riding along with the neighbor galaxy that hides it. If a dwarf galaxy like the Large Magellanic Cloud has been quietly cradling a supermassive black hole this entire time, it is highly likely that countless other small, ordinary galaxies harbor hidden giants too. For most of the history of astronomy, finding an object meant seeing its light. You pointed a telescope and waited for something to glow, or you watched it block the light of something behind it. But this black hole gives off absolutely nothing we can catch. It has no glowing accretion disk, it is not feeding on nearby gas, and it remains completely dormant in the dark. We are stepping into an era of cosmic forensics. We are learning to identify the most massive objects in the universe purely through the gravitational wreckage they leave behind. Even the darkest objects in the cosmos betray their locations, revealing themselves through the specific trajectories of the victims they cast away.